A report on the topic is offered to your attention: drainage reconstruction in the zone of excessive moisture during the cultivation of blueberries on poorly water-permeable clay soils. Authors of the report: Klimov Sergey and Klimova Anastasia from the National University of Water and Environmental Engineering. To ensure efficient agricultural production in the humid regions of Ukraine, the drainage of waterlogged lands occupies one of the first places. The area of drained land in Ukraine is 9.7% of the total area of arable land. In 1990, 1,976.5 thousand hectares were used in active agricultural production, and the proportion of arable land on drained lands was 70.7%. Of the more than 1.13 thousand built drainage systems with an area of more than 2.2 million hectares, only 37% were built from 1980 to 1990, that is, today they are less than 35 years old. The remaining 63% of the systems have been built and have been in operation for over 35 years. Since the 1990s, the construction of new and modernization of existing drainage systems has not been carried out. Operational activities on already built systems have been significantly reduced, which led to a change in the water physical properties of soils and the development of degradation processes. In Ukraine, a significant, 1.4 million hectares, area is drained by pottery drainage. The work aims to describe the reasons that led to the negative technical condition of drainage in the zone of excessive moisture in Ukraine and also describes a new approach to drainage renovation. With limited funding on the example of reconstruction of drainage system, the cultivation of blueberries on poorly water-permeable clay soils. To achieve this aim, the following tasks were set, taking into account the agro-soil, topographic, hydrological and climatic features of the territory of the study area. Determine the causes of local waterlogging, which lead to a decrease in the yield of blueberries. Choose the most optimal way to localize the identified malfunctions of the existing drainage. Describe the technology of renovation of the drainage system by the method of building a new drainage against the background of the maximum preservation of the efficiency of the existing drainage system. For the successful use of the territories with built, but faulty drainage, it is necessary to carry out restoration work, which will ensure the optimal water regime of soils and, accordingly, agricultural production at the required level. The priority tasks of the comprehensive program for the development of land reclamation and improvement of the ecological condition of irrigated and drained lands are restoration of the functioning of reclamation systems that are in an unsatisfactory technical condition, but have not yet lost their potential, through the reconstruction and technical re-equipment of the on-farm system, which does not need significant capital investments. The task was to ensure the sustainable functioning of the existing 3.15 million hectares of drainage systems. To reconstruct the drainage systems and improve the ecological condition of drained lands on an area of 46,000 hectares, and from 2006 to 2010. Another 134,000 hectares, total 180,000 hectares. However, insufficient funding of both the program, out of the envisaged 6.7 billion Ukrainian hryvnias, actually 5.1 billion Ukrainian hryvnias, or 76.1%, was allocated from the state budget, and the entire structure of the state water agency led to the failure to fulfill the tasks set for the reconstruction of reclamation systems. Fixed assets, minimum in 2006 to 76%, maximum in 2016 to 96%, and on average for 2015. 2021 to 93% of the funding of the state water agency included in the state budget of Ukraine are spent on the operation of national and inter-farm state drainage systems. However, 36.45% of them are spent on wages, another 31.43% is spent on utilities and energy, and development costs are only 0.7%. Taking into account these amounts of funding, the possibility of reconstruction of the drainage systems is in rather small volumes than it have to be expected. Further exploitation of the lands of a particular drainage system without its reconstruction will lead to significant material losses or endanger the population as flooding houses and structures, polluting drinking water, etc. Consequently, the urgent need to carry out work to restore the functioning of the drainage on the one hand and the lack of funding on the other, encourages finding new approaches to drainage renovation, different from the option of building a new drainage network. In particular, it is proposed to carry out work on the partial reconstruction of areas whose damaged drainage, according to observations, leads to crop losses, and to leave the drainage that performs its functions. This paper shows an example of the reconstruction of a drainage and moistening system with an area of 39.9 hectares for growing blueberries. The blueberry bushes are irrigated by a drip irrigation system built in 2019, and drained by a ceramic drains built over 35 years ago. On Figure 3 shows the data for the reconstructed drainage area in terms of precipitation, as well as the maximum, average and minimum moisture values of the surface soil layer and the root zone for the period 2016–2021. Also, in recent years, there has been a tendency for an increase in the frequency of cloudburst, which significantly changes the conditions for the operation of drainage. To find out the reason why the drainage system built more than 35 years ago does not adequately drain excess groundwater over the entire area, which causes local waterlogging of crops. Field and in-house studies were carried out in 2020–2021. The following causes of waterlogging have been found: the presence of a large number of closed depressions, in which meltwater and storm water stagnate, which is due to the accepted agricultural technology for growing blueberries and the existing relief. Heavy mechanical composition of soils with a very low filtration coefficient, 0.01. 0.005 meters per day, against the background of a generally high annual precipitation rate. There is a tendency for an increase in the maximum frequency and intensity of precipitation, which, against the background of a low infiltration capacity of soils, cause a high standing of the groundwater level. To find the actual location of the drains and compare them with archival design data, we abandon traditional search methods, excavation and manual search, and terrestrial geophysical methods, including magnetic gradiometry and ground-penetrating radar (GPR). Therefore, visible (VIS) satellite images of the site of different years were analyzed. Multispectral (MS) and thermal infrared (TIR) images, as recommended when using of unmanned aerial vehicles, UAVs, were not used due to the low resolution of available satellite images. Satellite images also make it possible to identify problem areas in which drainage does not fulfill its functions or relief features create local zones of systematic waterlogging. In such zones, the vegetation has an excellent color which is especially evident when using multispectral, MS, images. For example, in the image NDVI, normalized differential vegetation index, B8A-B04, B8A plus B04, zones in which NDVI index is 0.35 are clearly visible. While zones with unoppressed vegetation have NDVI index from 0.5 to 0.6. After identifying the causes of waterlogging, the state and location of the existing pottery drainage, it was proposed to reconstruct the drainage network by installing additional drains in places of the greatest waterlogging. To prevent the destruction of the existing pottery drainage, the depth of laying new polymer drains is taken at the level of the soil freezing depth, 0.7 meters, for the given area. This is on average 0.2 meters higher than the existing pottery drains. Drainage pipe PVC DN50, drainage, and DN100, collectors, was protected from silting by gravel filling, fractions 5, 20 and 20, 40 mm. The filter bed was placed in a pocket, made of thermally bonded Typer SF27 geotextile. The tube was laid on a layer of crushed stone, which was poured on top of the geotextile to increase water susceptibility. The geotextile was wrapped around the drainage filling at 0.2, 0.3 meters from the soil surface, and the trench was further covered with crushed stone. This was done to protect the geotextile from being torn apart by agricultural implements during tillage. Conclusions. In Ukraine, as in a number of other countries, 5, 6, a significant number of drainage systems are operated, which, due to climate change, failure of individual drainage elements or a change in the purpose of the territory, do not fully provide drainage functions. With limited funding or in other cases, for example, if there is a desire to preserve perennial plantings, only part of the drainage system may be reconstructed. In this case, it is important to accurately map the existing drainage lines, find the places and causes of local waterlogging, and insert additional drainage with the possibility of intercepting the drainage flow from the existing one.